Okay, here we are, sections 25 and 26 this week. Shouldn't be too bad, hopefully just two sections. And they really go together. So just two sections of web work this week. We do have an Excel assignment with trend lines. I do have an old video, so when I post this live recording, I will also post that Excel help video, short quiz over linear models, and then a discussion board. So kind of it's kind of a light week, it seems like. But anyway, so Matt, you are currently the only one here. So do you have any questions before we jump into the mathematics of section 25? Okay, in that case, we'll just roll. And I only have three examples from section 25 loaded in. So at the end of those three, if you would like another one or something like that, I can make one up as we go, or if you feel good, we'll kind of move on from there. So just kind of let me know what you need as we go through. Okay, so here in section 25, we get into linear models. And when we talk about linear models, we talk about slope and y-intercept. Those are kind of the two big pieces of a linear model that we're going to get to. So when we talk about slope, we're talking about the constant change. So something that, wow, my handwriting is super bad today. Constant change. So something that happens over and over again, the same amount all the time, would be considered our slope. We can find the slope through two ordered pairs by taking y2 minus y1 and dividing by the difference of the x's, or x2 minus x1. Now, the little sub numbers here simply mean that our ordered pairs would be x1 is paired with y1, and x2 is paired with y2. So those little numbers just signify an ordered pair. So you can see the ordered pairs are stacked up on top of each other. So these ordered pairs are any two ordered pair that fall on the line. You can find the slope through that line using this piece. Slope is generally denoted by the letter M. So when you see the formula for the linear model, M implies the slope. So sometimes they'll just tell you, you save $10 a month. Well, every month you save $10. That's a constant change. That would be your slope. So sometimes you're just given the slope. Sometimes you're actually going to have to find it. Depends on the problem. All right, so then we go to the y-intercept. The y-intercept is kind of a one-time thing, and we often talk about our y-intercept as the starting point. So if you're graphing a line, which we don't do by hand, we will do that in Excel, but if you're graphing a line, the y-intercept is where we start by hand, because the y-axis, right, which is the vertical axis, right, so we graph, right, this is x and this is y. There we go. The y-intercept is any spot on this line, where your graph crosses. So this right here would be our y-intercept. If you have a straight line, it can only cross the y-axis in one spot, right? Unless it's a vertical line on the y-axis, and that's a whole different ballgame. So the y-intercept is noted by the letter B. I don't know why, it just is. And one thing that has to be true, if you go back to this little drawing, let me change colors just for effect. If any point on this line, think about the x value for that. You're not moving right or left at all. So the x value for any y-intercept, x has to be 0. So the ordered pair would be 0, b, where b is the actual y value of the y-intercept. So when you're looking at ordered pairs and trying to figure out which one is your y-intercept, it's whatever has an x value of 0. That's how you know where your y-intercept is. Okay, we put those two pieces together to create our model, y equals mx plus b, where m is our slope, b is our y-intercept, and the x and y in this formula will always remain x and y, and though that x and y represent any point on the line. So if we go back to this picture, any one of these points has an ordered pair of x, y, right? x1, y1, x2, y2, x3, y3, blah, 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 goes on and on and on. So that x and y represent any point that falls on this line with the appropriate slope and the appropriate y-intercept. So that's kind of the background information of section 25. And now we're going to get into some math problems with it. I have found in the past that the more you do of these, the easier they get. So we're going to do 3 problems here in this live session. And then I do recommend you work through the packet and kind of work through all of the examples in the packet. And even the ones in the back of the packet might not be a bad idea for this section, because the more you do, the easier they get. So, okay, let's go ahead and move on to the, whoops, I get excited. All right, so this is a multi-step problem, and there's some different pieces to it. So the cost of a cell phone plan is $300 a month plus 10 cents per minute. And we are going to focus on just 1 month. So we're not talking about the entire year or anything crazy, just 1 month. So when I look at this problem, or I guess when you look at this problem, and we have a cell phone plan that's $30 plus 10 cents per minute. We're trying to differentiate those values. One of them is the slope and one of them is the y-intercept. Any idea on which is which? The slope is 0.10. Why do you say that? I mean, you're correct, but why? Because it increases for every minute. That is correct. It's a constant change. Every minute that you talk, you have another 10 cents. So because that is a recurring charge, that is the slope. So yes, so we will know that the slope is 10 cents. Right, so every minute. Good. So for every minute, we have a 10-cent charge. Good. And I'm repeating everything you say because when we post this, the chat box does not come along. So it's good if people can hear your responses. Okay, so what is the y-intercept then? Yes, the $30. Because if you think about it, you have a $30 flat fee. Even if you don't talk on your phone 1 minute, you still owe $30 because that's kind of your base fee. So your one-time fee is $30, and then you paid 10 cents after that. Okay, so because we have our slope and our y-intercept, now we can write our linear model. We always start with y. Our slope goes in front of our x value, and we have plus 30. So this yellow goodness is our linear model. So once you have the slope and the y-intercept, it's pretty easy to kind of put those pieces together. But you have to have the slope and the y-intercept first. Okay, now letter D is not necessarily a question that you always need to, you won't need to answer like in web work or anything else, but it's a question that you kind of want to ask yourself and have in the back of your head. You always want to know what X and Y represent, because like in E and F, we're going to start doing some mathematics with these models. And if you're not sure what these variables represent, it's very hard to play with them. So in this particular case, do you have any idea what X represents? What does it stand for? And sometimes it helps if you look at your slope. What does your slope represent? You can kind of go from it. Yeah, X is how many minutes. And if you think about it, right, we're talking 10 cents per minute. Well, so X represents the number of minutes. Number of minutes. And what about Y? Can you think through about what Y equals? Right, Y is all of this crap on the right side together. If you put all of that together, the total cost. Exactly. The $30 base cost plus the cost per minute. So it's always good to kind of have in your mind what those variables represent, because it'll make your life easier later. So when we move to letter E, and it says, what is the monthly cost when you talk for 76 minutes? Well, 76 minutes is X. So I'm going to say, okay, that means X is 76. And we use our model, Y equals 0.10, right? 10 cents times 76 plus 30. You just have to make sure you use your order of operations. All right, remember that you always will multiply before you add. And so if you talk for 76 minutes, what is the total cost? $37.60 is correct. $37.60. There you go. All right. Now you can also go the other way. So looking at letter F, Now we know the monthly cost is 43. Well, remember the total cost is y. So now that 43 gets plugged in for y, and we have to work backwards. Well, this is very similar to when we solved proportions and we had to solve those equations, right? So we split the equal sign left and right. We want to get x by itself. So whatever is touching x is the last thing we're going to deal with. So my first step is to subtract 30 from both sides, because 30 minus 30 will make that go away. And I'm left with 13 equals 0.10x. And because that 10 cents is touching the x, right, that means multiplication. And so the opposite of multiplication is division. So we divide both sides by 10 cents, and we end up with 130 minutes. Okay. Questions about that? Okay, I feel like this type of problem is very straightforward, right? They give you the slope and the y-intercept. You just have to be able to identify which is which. And once you have that rolling, it's really not too bad. So we're only going to do one like that because that one's not too bad. Okay, oops, wrong button. There we go. Okay. So now we're into the second type of problem. The population of a town in 1970 was 5,600, and in 1995 it was 4,100. So you'll notice right away they give you two pieces of information, but they don't really tell you, they don't give you a slope, they don't give you a y-intercept. So in order to create a model, we know we need a slope and a y-intercept. So I have to find those. But if they don't give them to you, you need ordered pairs in order to find them. So one thing to remember, let me do a little drawing here. And actually I'm going to go back. Crap. You'd think I would have this stuff figured out by now. Okay, so I just want to draw this picture, right? So this is x and this is y. X is known as the independent variable, and the y values are the dependent variable. Okay, and we get more into this in section 26. But the independent variable, the x value, when possible, it's always time. So if you have a problem that has anything dealing with time, whether it's seconds, minutes, hours, years, age, because technically age is a part of time, anything like that, it's going to be the x value. If you don't have time as part of your problem, then you got to think a little harder. But if you have a problem and they talk about time, then you can just roll with it. So when I look at this next problem, you'll notice they talk about years, 1970, 1995. Those are years. Years are time. So I have two ordered pairs. The first one, in 1970, the population was 5,600. And in 1995, the population was 4,100. Okay, well, great. Do you notice a problem? Because our ultimate goal here, letter C, I would say is our ultimate goal. We want to write a linear model. And remember, for a linear model, we're going to need our slope and our y-intercept. It's okay if you don't know the answer to this. Do you see any problems with our ordered pairs the way they are written? I mean, mathematically, they are technically correct, but they are limiting in the way that they are written. True that we don't have a slope yet, but through those ordered pairs, we could find our slope. Think about the y-intercept. What must be true in order for us to have a y-intercept? This is one thing that you kind of got to keep in the back of your head always. In order to have, right, we need a starting point. And if you think about it, we are totally going to build on that. To have a y-intercept, right, we need an x equals 0. Because the starting point, as you mentioned there, the starting point is x equals 0. That's where we start. Well, in this problem, we're not starting at 0. Neither one of our ordered pairs have an x value of 0. So we can play a game, right, because math is fun. And we say, okay, if I look at my 2 years, I have 1970 and 1995. The earliest year that I'm given is 1970, and therefore that is my starting point. 1970 is my starting point. So I'm going to rewrite this ordered pair with a 0 as 1970. And I'm going to erase a lot of this stuff because I want to write more. So basically the game is we're going to let 1970 be x equals 0. Okay, this is kind of, and sometimes if you're a visual person, it will help to write this out. And so if we play that game, think about then 1995. How far is it from 1970 to 1995? How many years are between those two? 25, exactly. So if you're saying in 1970 x is 0, then 25 years later, x is 25. And that's kind of how this rolls, right? So now I have a new ordered pair, 25, comma, 4100. So they might give you the values in yellow, which is what this problem gave us, but because we need a y-intercept, we have to change them so that one of our x values is 0. Okay, mathematically, that's kind of the way this rolls. Okay, I'm going to get rid of these drawings and rewrite. Okay, so we have the ordered pairs 0, 5600, and 25, 4100. Based off of this, if you look at your first ordered pair, we now know that our y-intercept is 5600. Okay, so we have just completed letter A, which was create two ordered pairs, one with an x value of 0. If you need to write a linear model, one of your ordered pairs has to have an x value of 0. Okay, so then let's go to letter B, which says find the slope, which we have not done this yet. I mean, we were given slope in the last problem. So remember that slope is going to use the y2 minus y1 over x2 minus x1. Now, it doesn't matter which one you label which. I usually just do in order. Whatever I see first, I make 1. Whatever I see second is 2. Oop, that's a y. But mathematically, it doesn't really matter. You'll get the same answer either way. So when I throw my numbers in, if I start with y2, well, y2 is 4100. y1 is 5600. The key is that your y values have to be on top, and your ordered pairs should be on top of each other. So because I started with 4100, which is y2, the bottom I want to start with 25. And I'll take 25 minus 0. And that's we're given. And this formula, y2 minus y1 over x2 minus x1, that is on your yellow formula sheet that you will be given for the third exam. So you don't have to have it memorized or anything. And just make sure you reference it so that you don't forget the y values are on top. Okay, so that gives me negative 1500 over 25. So my slope in this case is negative 60 over 1. And you can simplify that to just be negative 60. There's nothing wrong with that. So basically what that means, right, our population is decreasing. I know it's decreasing because I have a negative slope. So my population is decreasing by 60 people every year since 1970. And I know it's since 1970 because that's my starting point. Okay, so that's slope. Is everything making sense so far as we're working through this problem? Okay, good. All right, so now that we have our y-intercept and our slope, now we can write our linear model. So again, we always start with y equals our slope, which is negative 60, goes in front of x, and then our y-intercept, in this case it's positive, we're talking about people. That is a really nice plus sign, plus 5600. And there is our linear model. And the y equals mx plus b is also on your formula sheet, so you don't have to have that memorized either. Okay, so far so good. So now in letter D, we want to use that linear model, so the y equals negative 60x plus 5600, to predict the population for 2017. So the key is you have to decide what is your x value in 2017. So remember, in 1970, x was 0. In 1995, x was 25. So what will it be in 2017? So you always can kind of think, 2017 minus my starting point, which was 1970, is how many years? $47, exactly. So my x value is going to be 47. So I take my model, y equals negative 60 times 47 plus 5600. And what do we get? $27.80 is correct. So if it continued with this trend of losing 60 people a year, in 2017 we would expect this town to only have 2780, right? And eventually, if you think about it, if it loses 60 people every year, eventually there will be nobody left in this town, because eventually they will run out, right? Okay, let's do one more of those. The state of Indiana has set a goal of 60% degree attainment among adult Hoosiers by the year 2025. That's only part of the problem. Part A is the other one. If the percentage of Hoosier adults with degrees was 33.2% in 2010, construct a linear model to estimate the goal for each year. Okay. I would like you to try this on your own. So I'm going to give you a few minutes. And since you're the only one here live, you can tell me I'm lost, I have nowhere to start. You just communicate where you're at, what you're doing. But I want to give you a few minutes to at least try it on your own to see if it makes any sense. So do you at least know where to start or have an idea of what to do? Okay. So you let me know when you're ready. We'll kind of roll with your time frame. I'm going to stop the recording until we come back. There we go, recording. Yeah, and you even left it in terms of a fraction. That is fabulous. Very good, very good. Okay, so now for on the screen so people can read it. So we have two ordered pairs, right? 20, 25, 60. And the other one is from down the problem, 2010, 33.2. Well, you look at it, you say, nope, can't have that, need an ordered pair. So 2010 is our starting point, so that one becomes 0, 33.2. And this is 15 years later, so I have 1560. To find the slope, y2 minus y1 over x2 minus x1, and we get 26.8 over 15. You can change it to a decimal if you want, or you can leave it as a fraction like you did. That's perfect. And then your y-intercept is 33.2. That red is a little bit hard to read. Okay, so our model becomes y equals 26.8 over 15, if you keep it as a beautiful fraction, plus 33.2. Very good, very good. Okay, then part B says use that to predict the percentage of degree attainment for the year 2016. What value of x would you use in 2016? 6, exactly, because 2010 was 0. So 2016 is 6 years later. So you'd plug 6 in, 26.8 over 15 times 6. I'll use it multiplication dot, plus 33.2. And I didn't do an exact answer, I did a rounded answer, so I'm going to go ahead and do the exact. There we go. Exactly. Y equals 43.92. And technically it would be a percent because we're talking about our Y values are percents in these problems. So 43.92% would be the estimated or the predicted percentage of degree attainment, assuming that we're making progress in a timely manner. Yeah, very good, very good. So that is section 25 in a nutshell. And section 26 kind of builds on that a little bit. So you did great on that. So I think that you're probably good. 26 throws in the idea of trend lines and linear correlation coefficient. And a trend line is really, it's a linear model, is exactly what it is. So let me get colors here because I can't talk without color. So if we have ourselves a graph, pretend that's a vertical line because it was supposed to be. A scatter plot really is when you graph data all over. So pretend these orange dots are data. A trend line is a linear model that cuts through basically the center of the data. So pretend that's a straight line. Lots of pretending happening today. And the purpose of trend lines is because you can't predict if you have data all over the place. How do you know if it's going to be up or down or whatever? But if you throw a trend line in there, that now gives you constant change over time. It kind of gives you the general feel, right? The average of what's happening. So that's what a trend line is. It's the linear model that cuts through a scatter plot. And you can do it by hand, but it's a pain in the rear. But Excel is beautiful, and Excel will do it. And I'm actually going to do a little example in Excel here in a moment. So if you are in Excel and you throw up a scatter plot and you put a trend line in, Excel will actually give you the equation for this. So I just am making up an equation because that's what I do. These might say, hey, there you go, blah, 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 blah. And then it will also say R squared is, I don't know, 0.7132. I'm just making this up off the top of my head. So the trend line is what we've already dealt with, right? Y equals mx plus b, slope, y-intercept, got it, great, good, love it. This R business is the new piece. So the linear correlation coefficient, I lovingly refer to that as the LCC because I'm lazy. The linear correlation coefficient is denoted by the letter R. You'll notice that up here, we are given R squared. Well, R squared is the coefficient of determination, which shows other stuff that we don't have to deal with. We're not worried about R squared in this class. We only want R. So do you have any idea how we can go from R squared to R? What do we do to unsquare the R squared? We take the square root. Exactly. So we are going to take the square root of both sides. So if I take the square root of 0.7132, I get, for this particular example, 0.8445. Now, when you take the square root of R squared, it's always going to be positive in your calculator, always. But you have to pay attention because, like, my line here that I drew is positive, right? It's going up. We have a positive slope. The sign of your linear correlation coefficient will always match the sign of your slope. So if you have a positive slope, you have a positive LCC. If I had graphed a line that went down, so I had a negative slope, then I would have a negative R. Right? So those signs have to match. So that's one thing to make sure you're paying attention to, because your calculator is not going to give you the negative. You're going to have to throw that in there. That makes a difference. Okay, now the purpose, because you're like, that number means nothing. True statement. The purpose of the linear correlation coefficient, the R value, it shows you how good of a fit your trend line is to your actual data. So the closer your R value is to 1, the more linear your data. And there's a great spot. I don't have my packet open, so I don't remember what page it's on. But there's a couple of really good graphics in your packet that talk about the R value. So if it's positive, it's going to be, so R is going to be somewhere between -1 and +1. Okay, I should have put the r in the middle, not 0. My bad. But it's positive, right? If you have a positive slope, and it's negative if you have a negative slope. If it's exactly 1, that means your dots are in an exact straight line. Going this way. If it's negative 1, that means they're in an exact straight line going this way. Real life is not linear, right? So we know that it's probably going to be closer to, like, 0.8 or 0.9. So what we would say, right, you can write meaningful sentences. You have to interpret your linear correlation coefficient. We would say there is a somewhat strong, because 0.84 is decently close to 1. So a somewhat strong positive, and I throw the word positive in there because that is the sign of my slope and my linear correlation coefficient. A somewhat strong positive linear correlation between, I don't know, X and Y, whatever your two variables are, right? I don't have any labels on this example, so I don't have anything for real here. But it's between your independent and your dependent variable. Whatever those pieces are, you can show a linear correlation. That doesn't mean that one is causing the other. That just means those two things are related in some way. It's really not anything about causation at all. Okay. Any questions on just the definitions of what that means? And that's another one that the more you do it and kind of play with it, the easier it is to remember. So you might need to play with that a little bit. All right. So we have, the only other thing I want to do in this, I want to do an Excel example. So I have some of it already up. So let's get rid of that. Let me bring up Excel. Okay, super big. You can see the Excel screen now, yes? Yes, okay, just making sure. Okay, so you're going to do an assignment in Excel that's going to be kind of similar to this. And I do have a video posted, so you can always watch that for reference. But I think it gives us another way to discuss slope, Y-intercept, the linear correlation coefficient, everything. So if you have your data, you always want your independent data to be on the left, right? So these are my years from 1999 to 2010. So years are time. Time is always independent. And then I have this business over here. I probably should give myself some labels. So let's call it years, and let's call it broken bones, because, that might be true for some people. Okay, so if I want to graph this information, I highlight it all, right? And to highlight it, right, we click and drag. Many people at this point in the semester are getting more comfortable with Excel, and that's fabulous. But when I click on the insert, right, you've got the charts here in the middle, and you can see this one that just has all the dots that is now highlighted. That's a scatter plot. So if I click on that, you can see it will give me scatter plots. And that's what I want. So this gives me these lovely blue dots that shows the number of broken bones per year. All right, and that's great, but I want a trend line. And if you were doing this by hand, you could take a ruler and line it up approximately, in the middle of your data and draw a line, but then you have to come up with two ordered pairs in order to find slope and Y-intercept, and that can be very difficult. So what we do is we click on it. Notice I just clicked on any one of these, but all of them are now highlighted. And then I can right click, and you can see it says add trend line. So that's one way to do it. I think you can also do it over here on the plus side. There's a trend line there as well. So either way, you have two different ways of adding the trend line, and it automatically throws in there for you, which is beautiful, right? So you'll notice that the trend line is a linear model directly through the middle of your data. You should have approximately the same number of dots above and below. It should be very, very close. But I now want to know, what is the equation of that trend line? Well, if I click on that trend line, there's a couple. Okay, I double clicked on it to make this format trend line come up. When I right clicked, you could see the format trend line down here. You get the same thing. When I look over to the right, you see it says linear over here, and there's all of these other trend line options. We always want linear because that's all we're playing with right now. But at the very, very bottom, you can see it says set equation on chart and displayed R squared value. What is this button? Oh, okay. And that's what I want. I want the equation, right? Y equals mx plus b and I want r squared. So when I did that, right, I can now get rid of that piece. I now have a linear model, and I have r squared. So you can see our slope is 0.7552. The number of broken bones approximately increases, right? It's positive slopes, we know it's increased. The number of broken bones increases about 0.75 for every year after 1999. Right, there's your interpretation of the slope. Now, I do want to draw your attention to the y-intercept at this point. You'll notice that the y-intercept is negative 1,493.6. Seems kind of crazy. Why is the y-intercept not, I mean, if you look at the graphic, my y-axis is you know, over here, by this line. Why is it not, you know, I don't know, 15 or so? Any idea? Why is it telling us that our y-intercept is 1493.6? Oh, perfect. Always remember, the tricky thing with the y-intercept, x has to be 0. And if you look at your x-axis right now, our smallest x value is 1998. 1998 is not 0. So because of that, they would have to take this line and go all the way out to year 0 in order to find the y-intercept. And they do that with the points negative 1493.6. Right? Now, we're going to come back to this in a second, but I want to show something because this is what I do. If I change this to be 0, 1, right? So if I play the game that make 1999 be x equals 0, and then we graph this, I add a trend line, just everything we just did, format that trend line. Notice how I have the exact same slope, I have the exact same linear correlation coefficient, but look at the difference in the y-intercept, because now my x value is 0. So because the x value is 0, that's where it crosses the y-axis. So you can kind of tell, you know, an equation that looks weird, and I say looks weird because a y-intercept of negative 1400 something is weird. That usually means that they gave you actual years as your x values. Whereas in sheet 2 here, we played the let x equal 0 for 1999. So if I wanted to do a prediction for a future year, it's different, right? If 0, 0 is 1999, then the year, why did I pick bad years? If 1999 is 0, then if I wanted to pick like 2012, x would be 13. Oops. Right? So that's how you would kind of think through. I would plug in 13 for x into this to find 2012. But in this one, if I wanted to find 2012, I would just type in 2012 for x. You'll get the same answer because the y-intercepts adjust for that in these two problems. Right? So same data, just I don't even know the word I'm looking for. Depicted differently. That's the word I was looking for. All right. All right. So if the r squared value is 0.8267, what is my linear correlation coefficient? So we're given r squared. The linear correlation coefficient we know is just r. Oh, don't worry about it. Okay, so if we take the square root of 0.8267, we end up with 0.9092. Right? You're good. You don't have to find a calculator. No problem there. Right? So because this again is a positive slope, because I don't know how to do anything negative. So a positive slope, so we have a positive linear correlation coefficient. 0.9 is getting really close to 1. So we would say there is a strong positive linear correlation between broken bones in number of years since 1999. Strong correlation between those. As time goes past, we're breaking more bones, right? That's kind of how this is. All right. Any questions on anything that we've talked about so far today? Because that's pretty much it. You seem to have a pretty good grasp. All right. So if you don't have any questions, then good to go. I will post this video and the Trendline video. So if you want to kind of watch it in more detail or whatever, that one, it's not very long, maybe 5 minutes total. But we'll have those two posted. And then next week, we've got sections 27, 28. Those are super, they'll go by probably quicker than this one did. And then the following week is final exam. So if you haven't scheduled your final exam for 2 weeks from now, I would do that, because remember, every online class at all is going to be taking an exam, and you're going to be fighting for spots in the testing center. So figure out what day and time you want to take it. I would get that scheduled ASAP. To make your life a little bit easier. So I'll be posting an announcement about that probably maybe tomorrow to remind people as well. So, all right. So if you got nothing else, thanks for coming, and let me know if you have any questions as you're working through the homework.